To introduce the last talk of this morning by Yuval from Microsoft at Redmond. The title is Concentration of Lipschitz Functionals of Determinantal and Other Strong Rayleigh Measures.
Good morning, almost afternoon, and it's a real pleasure to be here. So this talk, so I'll abbreviate as concentration with Lipschitz functions, or of Lipschitz functions with negative dependence. So this is joint work with Robin Pimentel. And so Devdat earlier today mentioned the issue of getting concentration for functions of negatively dependent processes, and that's what I'll focus on. Our initial motivation came from a question of Elchanan Mosel that we heard from him, which is consider I'll be more precise, and he was more precise, but for now I'll just write a negatively dependent process of, so this is, or negatively dependent variables, x1, x2, up to xm. So these are 0, 1 valued. F from 0, 1 to the m to r is one Lipschitz function. So of course that just means that if we have two vectors, say x and y in two binary vectors, and then the distance between f of x and f of y will be bounded by the Hamming distance of x and y. And the question is f of this vector x1 to xm concentrated? And a concrete example, which we'll also use as the main example in the discussion, is take G graph with m edges. T is a uniform spanning tree in G. Later we'll also consider weighted spanning trees, but now just think of a uniform spanning tree, so all spanning trees taken equally likely. And then xi just measures is the indicator that we took the ith edge inside T. So it's classical, going back to the 19th century, even to Kirchhoff, that there is some negative dependence here to Kirchhoff and Rayleigh. For pairwise negative dependence, there's a stronger negative dependence in Burton Pimentel 93, who showed that this is a determinantal process. I'll mention this exactly, more precisely. And there's also a precise negative dependence or negative association result in this paper of Feder and Michal from 92, who showed negative association for this and other balanced matroids. So this is the example, and then we can take various Lipschitz functions f. So good examples to think of. So f of x could be the number of leaves, right? So if I see x, that tells me what is the tree, and I can ask for the number of leaves of the tree t. Or I could take f of x to be, for instance, half the number of vertices of t of odd degree. In various, this is, the motivation was connected to some of the recent works on the traveling salesman problem that employ picking a spanning tree, some weighted spanning tree, as a first step, and then completing it with a matching. So you care about the number of vertices of odd degree. So these are Lipschitz functions that occur in these applications. So there are relevant works of Saberi, of Escaran, Madri, Singh, and so which employ this as a step in algorithms for traveling salesmen. So this is an example, concentration of these variables, and the answer is positive for this example, though we still don't know concentration for Lipschitz functions of any negatively associated process. But I'll discuss these negative dependence properties soon. Now, so I'll give more background examples, but let me first just state one theorem. And to get to that, I need our key negative dependence property, which is in this paper with Pimentel, and that's the stochastic covering property. So first, okay. So first, I want to recall. So a strengthening of stochastic domination. So we say that measure nu1 stochastically dominates nu2. So there are various equivalent definitions. This is stochastic domination. So stochastic domination is equivalent to there is a coupling of the two measures, which is supported on the set of vectors xy with x greater or equal y. So this is one of the equivalent versions due to Strassen's theorem of stochastic domination. I can couple them so that the variable with distribution nu1 dominates the variable nu2. Now, I'll want to define nu1. So nu1 covers nu2 by 1. So I want to define this notion. This will be defined if there is a coupling on the pairs xy where x is greater than y by 1. And the last thing I need to define, x greater than y by 1, means this means that x is greater than y, but their Hamming distance is just 1. So they just differ in a single bit. Okay. And finally, nu has the SCP, so a measure has a stochastic covering property, what it means is if x is dominates y by 1, if x dominates y by 1, then if I take the measure and condition, say, x on some set x to be equal to x, so I'll write it this way, nu conditioned on the variables on some set S to be equal to x, this should be dominated by 1 by nu conditioned on x sub s equals y. There is stochastic covering property means there is some compensation. So let me make this more concrete in the case of the spanning tree. So let's take a graph. So the spanning tree is our prime example of the stochastic covering property. And so suppose we want to look at the uniform spanning tree of this graph. So suppose we condition on this edge being in the spanning tree. So I want to look at the UST of this graph, but with the blue edge. So the blue edge. So the blue edge has to be in the UST. And then what I'm claiming is that this is, if I ignore the blue edge, this is going to be dominated by 1 by the UST of the graph with the blue edge removed. So here I'm insisting on this edge not being in the tree.
When you say x dot bigger than y, do you mean restricted to s?
So x and y, I should have emphasized. So x and y, you see xs equals x. So this means x and y here are in 0, 1 to the s. Thank you. Okay. So I have vectors x and y which are just restricted, just defined on s. Okay. And x is bigger than y. So x is bigger than y by 1 on s. Now I look at the complement of s. I look at the other variables, and there I want the relation to reverse. So on the other variables, I can complete the vector so that on the other variables I'll have the measure bigger by 1 in y when I conditioned on y than when I conditioned on x. Let me explain this in the context of the spanning tree to make it more concrete. Suppose I condition the spanning tree to contain this edge. Then on the remaining graph, I'm going to so it has to contain this edge. So on the remaining graph, I'm not going to get spanning tree. I'll get I'll get a subset. In general, it's a forest because these two have to be in different components. So the spanning tree in the original graph, the spanning tree had here has 3 edges, and once I condition on this edge being in, I have 2 edges left to select. On this side, I conditioned this edge not to be in, so I still have 3 edges to select. And the statement is that I can do that in such a way, I can pick this little forest here, so the 2 missing edges here, and the 3 edges here, in such a way that these 3 edges on the right, the spanning tree on the right, will always contain the 2 edges on the left. I can always do that. So that's a property of the uniform spanning tree that's, in fact, so Feder and Michel proved that uniform spanning trees and other balanced matroids have the negative association property, but if you look in, they didn't define the stochastic covering property, but in fact, the first half of their proof entails proving the stochastic covering property, and that was the tool, and then in the second half of the proof, they deduce the negative association property. So I'm not, so... Yes.
Stochastic covering implies a negative association.
Stochastic covering together with homogeneity. So, so at least in the first part of the talk, most of the talk, I'll limit myself to homogeneous measures, which means the total number of ones is fixed to be some number k, as we have in the spanning tree. But in general, we care about negatively dependent measures without this condition, but this condition simplifies things a lot. And so...
Sir, more basic question. What's the
Yes.
quantifier on S? Is this
So thank you. This is for any set S. So for any set S which is a subset of 1 to m. Okay. So this is a property of the uniform spanning tree, which is the stochastic covering property, and that's now there are many other measures that have the stochastic covering property, and I'll tell you about this definition more precisely later. But maybe I'll put another class here. So we have here balanced matroids. So balanced matroids, you just, besides the matroid, so you look at the set of collection of bases of a matroid, and besides, so that's automatically homogeneous, and you just insist on pairwise negative correlations. And so balanced matroids automatically, so the theorem of Federer-Michal that balanced matroids have negative association property, as I said, the proof contains the fact that they have the stochastic covering property.
Did you define what negative association?
I didn't. I'm not explicitly using it, but let's still define it. So negative association for the variables means that if S1, S2 are disjoint subsets of the variables of the index set, then X restricted to S1, if I have some function f of this, and G restricted to S2, these are negatively correlated. So the expectation of this product is less than the product of the expectation for any f and g that are increasing. Okay, so positive association is the inequality going the other way, and there's no restriction that the dependence on the disjoint sets of variables. Now, of course, by Cauchy-Schwarz, any variable is positively dependent on itself. So in order to make this work for negative, one insists that the sets of variables are disjoint. Okay, so
here in this definition of SCP, these new are supported on S complement.
yes. So once so you condition on x equals s. Now you look at the distribution of the other variables. Yes, I didn't write that explicitly, but yes. So you look at the distribution of the other variables, and the other variables should kind of compensate. You have an extra bit in x, then on the other variables you should be missing a bit. So but you can't say which bit, right? So you have a coupling on the remaining variables that will be depressed by 1 if you condition on the variables in S to have an extra 1.
And the fact that the SCP implies negative association, is it immediate more, or is it
no, that's this. So in the homogeneous, okay. So in the homogeneous case, that's the second part of the Feder-Michael theorem. But for us, we don't need this implication, see, because we'll work directly with the SCP. So for us, the important thing is not negative association, rather it's the stochastic covering property itself. But okay, so so let me state already the theorem under the SCP. So, right. So if the law of the distribution of X has the SCP, okay. So the random variables, meaning their distribution, have the SCP, and I'm going to assume that the process is homogeneous. So the sum xi, I from 1 to m, equals some k. So this is what happens for us in the uniform spanning tree when k is, the number of vertices minus 1. And I said f is a 1 Lipschitz function on 0, 1 to the m. This is the main theorem of this paper with Martingale, or the main theorem in the homogeneous case. Then the probability that f of x differs from its mean more than a, so I'll just write the one-sided inequality, can of course reverse, is bounded by e to the minus a squared over 8k. Now, okay, so in particular, this implies the concentration for the spanning tree case. You take k to be n minus 1. Yes?
So the theorem doesn't generalize
To strong Rayleigh. No, it does. So SCP extends the strong Rayleigh. So this is more.
But you don't have this homogeneity first time.
So I said in the beginning, I'm stating the homogeneous case, and I'll come back to the non-homogeneous. But okay, let me. Since the question is raised, let me state the theorem for strong Rayleigh. So if X is strong Rayleigh, now what does that mean? Well, I'll just write the definition. It won't tell you anything about what it means unless you've thought about it before. So strong Rayleigh means that if you look at the generating function, psi of omega is some p of x equals, so I sum over all vectors in 0, 1 to the m, the probability that x equals omega times a z to the omega, so write product zi to the omega I. So I'm sorry, this is psi of z. So z is a vector of complex numbers, I from 1 to m. So this has no zeros in h to the m. H is the upper half plane. Okay, so suppose X is strong Rayleigh, which is now defined via this mysterious condition, which I'll come back to. Then, first of all, then X has the SCP. So if it's homogeneous, then this theorem applies. But if it's not even if it's non-homogeneous, we have a concentration inequality. So the probability that f of x differs from its expectation by more than a is bounded by, so e to the minus 3 e to the minus a squared over 16 a plus 2 mu, where mu is just the expected number of bits that are on. Okay, so I'll focus on the homogeneous case, and then I'll end with explaining what this strong Rayleigh property is. So let's see, I have my. Is there any questions so far on these definitions? Yes.
Would you get anything just from the negative?
Sorry?
Would you get anything just from the negative correlation at all? Like
Pairwise negative correlation?
Yeah, pairwise
Nothing.
negative correlation.
Nothing.
And is there other example of SCP?
So I have some examples here, which are so besides uniform spanning trees, any determinantal process. So any process where the probability there is. So determinantal just means if you ask what's the probability that the variables on some set S are 1, this is given by the determinant of some matrix, but restricted to the the S by S, only the rows and columns from S. So there is some matrix that satisfies this. So determinantal process, it looks like a very special definition, but besides uniform spanning trees, there are a wealth of other examples, many of them in the continuous realm, so eigenvalues of random matrices. And our paper has a continuous extension, but so it works for determinantal point processes, of which there's a huge variety, but today I'm focusing on the discrete case. So that's determinantal. So determinantal have the SCP, which includes the uniform spanning tree. I said all these strong Rayleigh have the SCP. They include, besides the determinantal, also anything you get by starting at a deterministic state or in the IID state and running simple exclusion, simple symmetric exclusion. They also include, here's a simple example, take Bernoulli variables and condition their sum to take a specific value. Okay, that's also strong Rayleigh. Another example is balanced matroids. So returning to the pairwise correlation, if you have the basis of, if you have a collection which is the basis of a matroid, like the uniform in the case of uniform spanning tree, you just have to verify pairwise correlations, and you get the stochastic covering property. So these are some examples with these properties. So I think it's fair to say most, but there are some other examples, but most negatively dependent processes we care about have the SCP.
So for general matroid, uniformly random basis, not SCP? For
No.
No.
We need that.
What?
Do we really need the homogeneity property, or?
Well, depending on what. So as I said, you can replace the strong Rayleigh. In the strong Rayleigh case, you don't need homogeneity.
With the stochastic covering, you don't need it.
Once you have stochastic covering, you don't need it, but you get a weaker estimate without the homogeneity. Okay.
Because this is a convex set, the measure which satisfies SCP.
Okay.
So I was wondering, what are the extremal?
Okay, so. All right. So. I want to indicate the idea of the proof and say something about strong Rayleigh, so I have to move on. So so let's recall the case of xi, IID Bernoulli. How is the concentration proved there? We start by taking, so suppose that xi is 1 with probability pi. We first observe expectation of e to the lambda, xi minus pi. So this is the usual e to the lambda squared over 8, right? So this is just so this expectation is just an average of two numbers. This is a classical, say, Hefferding inequality for these two-point thing. Everything can be written much more generally, and then you get from that expectation e to the lambda. If you look at the sum, so sum of xi minus pi. So let's call this sum Sn. So this is bounded by e to the of course m lambda squared over 8, and then you get from this that the probability that Sm is bigger than a is bounded by e to the minus 2 a squared over m. Okay, just by plugging in Chebyshev to that and optimizing for lambda. Now, this proof extends readily for partial sums of negatively dependent. More precisely, you just need cylinder negative dependence. So you just need a property like the expectation of the product of xi is less than the product of the expectations. This is called negative cylinder dependence.
For every s.
What? For every s, yes. If you have this property, then the proof goes through, and this property is weaker than negative association. But this is about the partial sums. So if we look at the classical situation, the most classical is partial sums of independent variables. There are two well-known extensions. One is to partial sums of negatively dependent variables, which just follow with the usual same proof. And the other is to Lipschitz functions of independent variables, which of course follow using the using the Martingale argument, for instance. So let's recall this. So if Mj is a Martingale with bounded gaps, so Mj plus 1 minus Mj is bounded by 1, then Hoeffding-Azuma, really Hoeffding, tells us that the probability that mk minus m0 is bigger than a is bounded by e to the minus a squared over 2k. Right, and then if you have a Lipschitz function of independent variables, you can just handle it using the Martingale you obtain by conditioning on the first j variables. So this is the idea we want to generalize, and that's where the SCP will come in useful. So,
actually, my question would make more sense if I asked if you have a sub-Martingale, like somehow all conditionals are negatively correct.
Maybe I'll come back to that later. So, okay. So we want to mimic this idea. So let's focus on this theorem for the homogeneous case. So a natural idea is to take again mj to be expectation of f of x given x1 up to xj. Okay. So if we have a Lipschitz function in the independent case, this Martingale will just automatically satisfy this. Now here we're not in the dependent case, but we can still do something similar. So let's look at mj minus 1, and I claim this is bounded by 2. Well, here's the definition of MJ. So to bound this difference, if you think about it, it's just enough to bound the expectation of f of x given x1 up to xj minus 1 and xj equals 1 minus the expectation of f of x given, again, the same values of x1, xj minus 1, but xj equals 0. If we'll bound this by 2, the other inequality will just immediately follow. To do that, we just can build, so we can build x star, which will have the following form, x1 up to xj minus 1. Then we'll have a 1, and we'll somehow complete it to xj plus 1 star up to xm star. And we'll build x tilde, which will have the same thing. But now we'll continue with a 0 and finish it somehow. So this will have the law of nu given x1 up to j minus 1 and a ending with a 1. And this will have the law of nu given x1 up to j minus 1 and ending with a 0. Okay, ending at the jth location is 0, so we complete it. And the stochastic covering property means that we can complete it so that this part and this part are closely related. So here they are separated by 1. Okay, so I can complete it so the remaining bits here are smaller, but by 1 from these bits. Okay, is this? I'm kind of compressing a lot into the notation here, but okay, is it clear? And now we're done, because if we look at this, can now be written once we have this coupling of variables with these distributions. Now it's just the expectation of f of x star minus f of x tilde. And x star and x tilde just differ by 2. So this is less than 2, just from Lipschitz. Okay, so stochastic covering property. So really making the right definition, does most of the work for us here.
This is actually way stronger than we maybe need.
Yeah, well, it's way stronger. It's also way weaker. So are we done here? Well, in the initial emails, we naively thought we're done here, but notice this is way off. So the concentration here is completely on the wrong scale. So think of the example of the spanning tree, right? So here we have concentration at scale m. So the fluctuations we can get are order square root of m, which in the case of the spanning tree, so think of a graph with the n vertices and n squared edges, and this will, so m could be as large as n squared over 2 or something, and then this will not give you this statement, but instead of the k here, you'll have an m. And that's useless. Unless the graph is sparse, that's useless, because telling me that the number of leaves on a spanning tree is concentrated, is about n with a fluctuation of about n is not very informative.
Because the Martingale, most of the jumps are 0. You're bounding the maximal jump, but not the average.
So one needs to use it. And the key is to use the right sampling procedure. And this is a very elementary point, but should be better known. So this point is emphasized in this paper on determinantal processes, where we were interested in sampling determinantal process. And so if you want to sample from a homogeneous measure, you can do it in k steps instead of in n steps. And not only can, you should. So what is the point here? Let's go back to spanning trees to make things concrete. Suppose I want to sample a uniform spanning tree. That case has many, many algorithms, beautiful ones, but I want to stick to the simplest algorithm. So here is one algorithm. Enumerate the edges. We have m edges. And for each edge, decide am I going to keep it in or not. So for every edge, the probability it's in, say initially, is just the effective resistance across the edge. So we don't need to use that for those who know it, right? So I can just decide, is this, so I have a graph, right? So I can just say, is this edge in? The probability is the effective resistance between here and here. When I send the unit of current between these two nodes, the effective resistance on this edge. Anyway, it's some probability. I decide whether to put this edge in or not with this probability. If I put it in, I might as well then glue these two vertices. If I decide not to have this edge, I might as well remove this edge and now repeat on a smaller graph. Okay, so this is an m-step algorithm of sampling a uniform spanning tree, requires computing effective resistance every step. We can and need to use a better algorithm for these kind of applications. So we know the spanning tree in the end will have n-1 edges. So let's first pick one. Let's pick the first one that will be in. So I don't want any edges to be told that edges are not in. I just want the optimistic information, which edges are in. So I'm going to pick the first edge to be in. How will I pick it? Just proportional to the effective resistances. So for every edge, or just proportional to the marginals. For every edge, I know the probability it's supposed to be in the spanning tree at the end. These probabilities, of course, add up to n-1. To the expected, the number of edges is going to be n-1. So I take these probabilities, I take the effective resistances, normalize them by n-1. Now I have a probability vector, and I pick the first edge according to these probabilities. Once I pick it, it's in. Now I delete and repeat. Okay, I contract. I glue the vertices. So I contract the edge and repeat. So I'll only have to do this k, which is in this case n-1 stages. And so all right, something has to go. So in other words, I can have a vector in the general setting. I can have a vector y1 up to yk. These are distinct elements of 1 to m, and in fact, the set y1 up to yk will be exactly the set of indices j where the xj equals 1. Okay, so knowing the y1 up to yk tells me exactly what vector x I want, because x is homogeneous. And that means that I can write f of x1 up to xk as some function, f hat of y1 up to fx1 up to xm. Right here I had m variables. It's a function just of these k variables. Okay, and now the right definition of the Martingale is going to be the expectation of f hat of y1 up to yk given, this will be mj, will be this conditioned on y1 up to yj. And again, one can check that it's still true that the same argument tells me that this Martingale is going to be differ by at most 2 at every step. But now I have only k steps. So that's why I get the k here. The 8 is because this Martingale differs by 2 at every step instead of by 1.
Now you need the stochastic covering of these wires.
But the stochastic covering here just follows from the stochastic covering of the x's. So when I condition on having, so this takes a few minutes of thought. But just if I condition on one more y, I just know the info. And this is because of this specific sampling property procedure of the y's. If I condition on one more y, then it's condition that I picked one extra location, and that turns out to be exactly the same as conditioning on that location being on. So this, there's something to check here, but it works, and it means this Martingale is at most differ by 2, so the argument works. So in the remaining 3 minutes, I want to. So I told you what determinantal is. many know what exclusion is. What is strong Rayleigh? Well, I wrote down the definition, but so this a polynomial with a property that has no zeros in the purely in the upper half plane with all the coordinates in the upper half plane. This is called the stable polynomial. This is a classical topic in the geometry of polynomials, and with various recent interesting applications. What does it have to do with negative dependence? So look at this generating function psi of z. The pairwise negative correlation has a simple interpretation in terms of psi of z. So if you look at the partial derivative, so I'll just write psi for the partial derivative with respect to the ith variable. So what is psi if you look at this function? If you look at psi of 1, so you differentiate with respect to the ith variable, and the effect is just insisting that omega I equals 1, because the contributions with omega I equals 0 vanish. So psi of 1 is exactly the probability that the ith variable xi equals 1. And so the pairwise negative correlations just means that psi of 1, psi j of 1 for I different j should be less than psi of 1 is 1, but I'm writing it here to keep everything homogeneous, times psi j of 1. So psi j of 1 is exactly the joint probability that both I and j. And here 1 is a vector of 1s, so I need all of them to be 1s. So this is just pairwise negative correlation. Now, in uniform spanning tree, one very natural thing is to put weights on the edges. And weights on the edges correspond to having, for real positive vectors x, psi of x, psi j of x, less than psi of 1, psi of x, psi j of x. This is for positive x. And this for positive vectors x, and this is known as the Rayleigh property. It comes from the fact the Rayleigh property, which is that when you contract an edge, you decrease all effective resistances. So this has led to this definition. And strong Rayleigh, so here is the theorem of Brandon, 07, is that strong Rayleigh is equivalent to this thing holding for all real vectors x. Okay, so you have to take psi and apply it to not just to positive vectors, which has a probabilistic meaning. You have to insist on it happening for all real values, and that turns out to be somehow the best notion we know of negative dependence. It's the most stable under various restrictions. So in the last minute, I want to explain something about this this connection, and then I'll be done. So we just say where this implication is coming from. So let's just see where this is coming from. So define for complex numbers u of v, define g of uv as psi of x plus uei plus vej. And because psi is multi-affine, it's affine in every variable, you can write GUV as A plus BU plus CV plus DUV, where these have just the meanings of partial derivatives. So explicitly A is psi of x, psi of x u plus psi j of x v plus psi j of x uv. So when you, because psi is not just a polynomial, it's affine in each variable, you have this representation. And the fact that psi is stable, has no zeros in the upper half space, implies that G is stable. So G cannot have zeros in the where both U and V are in the upper half space. So because if it did, then psi would have zeros where, they're in the upper half space with a few. Two of them are in the upper half space and the rest are real, and that would imply by perturbation some contradiction. So G is also stable, and so it has no zeros in the upper half space, but G is just a function of two variables. So these are the kind of functions one can compute explicitly. So where are the zeros of this? So you can solve when this equals 0. Right, this equals 0 when minus v equals a plus bu over c plus du. So what we want is, so we know that G is stable, meaning there are no zeros uv that are both in the upper half space. Now, what is this transformation? This is a Möbius transformation that preserves the real line. U goes to a plus bu over c plus du, preserves the real line. So it only has two options. Either it keeps the upper half space where it is, or it flips it. Right? Now, because of the minus v here, we know that in fact this must flip the upper half space. The other way. This must keep the upper half space in place, because this transformation, because minus v has to be on the other side. So now if you look, what is a plus bi over c plus di? Right, so you write it as a plus bi times c minus di over c squared plus d squared. And now you see that for this to keep the upper half space, you need here that bc should be bigger than AD. Right? That's the coefficient of I here, which is exactly BC. So is to keep. Right, so there is one thing here. So important thing, the direction of the inequality. So again, what is psi j? Psi j is the probability that both I and j are inside. So negative correlation means that this is less than that. So the end of the lecture. So so this is negative correlation means this inequality, and this is what we obtained here. So that's the way that the zeros are reflected in this. But it turns out that this is the right negative dependence property. To get the non-homogeneous case, one just uses the fact that the sum of the variables for a strong Rayleigh process is also concentrated, and then reduces to the homogeneous case. The details are in the paper, so let me stop now. Thanks.
Questions?
Can you replace K by the number of witnesses needed to witness that f of x is greater than certain amount? For example, if you're talking about the diameter of a random tree, can you replace K, which is n-1, by the diameter itself?
I don't think so.
This is the Talagram type.
I'll have to think about it more carefully. I can. Yes.
Are there any results where you get strictly better concentration than what you get in the independent case? Like, is there any condition under which you can satisfy the...
Not that I know. Let me emphasize that in this setting, the concentration necessarily can be worse. So if you have n independent variables, and then you copy them with negative signs. So you have x1 to xn IID, and then you just write them with just write the reflection. So this is a negatively associated and strong Rayleigh collection of variables. But now, if you have the function, the Lipschitz function, which sums the first n variables and then subtracts the next n variables, this is in effect doubling each of the two variables. So that's why the constant in the concentration inequalities in this generality has to be worse. So I wrote an 8 here. I don't know if this is sharp, but you cannot get the same concentration as for as in the IID case.
Proof seems to use only the absolute value of the differences and not the signs. So
Yeah, everything goes through to the.
So
Yeah.
it's not really about domination. The proof would work even if you could somehow couple it so that they're close by points.
Right.
If not, let us thank you again.